Right. Hello, everyone. I'm Alexander He. Today, I'll be presenting zinc oxide nanotubes for high-performance lithium-ion battery anodes, experimental insights from computational results. I'm from Mission San Jose High School, and I received lots of guidance from my mentor, Xiangao from University College London. So in this study, zinc oxide nanotubes were simulated and calculated to get their bandgap and density of states to predict their performance as anode materials for lithium-ion batteries. With the insight of reducing the bandgap by nanomaterialization to improve performance, zinc oxide nanotubes were fabricated with hydrothermal reactions. We tested performance after 100 cycles and confirmed that the nanotubes are better than bulk zinc oxide in many regards, including electron conductivity, bandgap, Coulomb efficiency, cyclic stability. An excellent reversible capacity of 861 milliamp hours per gram was achieved after 100 cycles at 0.5 milliamps per gram. Compared with bulk zinc oxide, nanotubes showed better stability and higher Coulomb efficiency. So in this presentation, I'll be going over battery anode materials and then zinc oxide nanotube modeling, experimental insights, and finally conclusions. So in today's world, batteries are essential to communication and productivity. They exist everywhere in phones, laptops, and cars, among many other places. In lithium-ion batteries, research into battery anode materials is especially important. The current industry standard for lithium-ion batteries uses graphite, shown in the second column, as the anode material. Graphite has a very low capacity of only 372 milliamp hours per gram, and the energy needs of society are starting to surpass what graphite can provide. Other materials such as silicon and magnesium have specific capacities in the thousands. However, it seems that there's a correlation between specific capacity and volume expansion, which hinders the effectiveness of the material. And thus, a possible solution that has been extensively researched is silicon combined with graphene. This takes advantage of the extremely high theoretical capacity of silicon of over 4,000 milliamp hours per gram, while introducing graphene to trap the silicon and prevent volume expansion. However, this option is still too expensive to begin mass production and be integrated into everyday items. Finding an environmentally sustainable and cheap option for battery materials that can still provide the required specific capacity, electric conductivity, and the lithium-ion transfer rate is a worthwhile goal. Metal oxides usually meet these criteria very well. We turn to zinc oxide as an option because of its abundance in the environment, its affordability, and its high theoretical capacity. There are many different types of anode material combinations with zinc oxide, each with its own advantages and drawbacks. Generally, zinc oxide anodes have a relatively high theoretical capacity of 978 milliamp hours per gram. Though not as high as silicon, it's still decent to consider for further research. As zinc is abundant on Earth and easily recyclable, it is a great material to keep the environment clean. Another advantage is that it has a higher lithium-ion diffusion coefficient compared to other transition metals. Some potential disadvantages are poor electrical conductivity, high volume change during charging and discharging, and poor cyclic capacity. So how do we solve the poor stability problem? So nanomaterials are preferred and have shown success in previous research because they increase specific capacity by increasing the surface area. It has been shown that zinc oxide can be made into many different materials such as nanotubes, nanospheres, and other shapes that improve its performance. This also helps counter the volume expansion of zinc oxide, which is 228% for traditional zinc oxide materials. We propose nanotubes, which are very tiny tubes of zinc oxide due to the success of previous researchers in finding especially promising properties that improve specific capacity and combat the weaknesses in zinc oxide. They increase the surface area that lithium can bond to, increasing capacity. They also help prevent the volume expansion of zinc oxide. In our study, density functional theory is used to calculate the band structure and density states of zinc oxide nanotubes. The anode with zinc oxide nanotubes is fabricated to test the results of the simulation and compare them to the cyclic performance of traditional bulk zinc oxide. The zinc oxide nanotubes were fabricated with hydrothermal reactions and exhibited excellent performance and cyclic stability, which should be used as a reference for future studies. So here are the methods we used for simulation and fabrication. First was density functional theory. In quantum mechanics, the density function of an electron is a function describing the probability of finding an electron at any specific location. As the density function is a function over the complex domain, the probability of finding it at a specific location is the norm of the value of the function at that location. The density function is given by the Schrodinger equation, which relates it with potential and kinetic energy. Our computation is based on density functional theory, which has gained popularity in recent scientific fields as a simple yet accurate way to do material energy level calculations. Density functional theory is used to analyze systems with a lot of electrons by reducing it to a function of the electron density function. Its accuracy has steadily improved since its proposal in 1964. Density functional theory is so alluring because of its low cost compared to other calculation methods and its wide range of applications across multiple scientific fields such as quantum physics, chemistry, and biology. For the simulation, we use the software Material Studios. And for the actual fabrication, we use hydrothermal techniques to create the nanotubes in the anode. The nanotubes are created in a chamber with very high pressure and temperature. One drawback of using this would be its safety concerns. Because it requires such high temperatures and high pressures inside the chamber, it must be kept very stable to prevent malfunction and explosions. So here's the model we put into Material Studios. The simulation of zinc oxide nanotubes are run to study their properties since it is a promising option. The zinc oxide nanotube model we created a single wall as shown in the figure. The nanotubes have a dodiagonal cross-section with a zinc and oxygen atom pair at each vertex. The bonds form a hexagonal shape with alternating zinc and oxygen atoms. Therefore, there's an approximately equal number of zinc and oxygen atoms. As shown in this figure, the zinc oxide single wall nanotubes exhibited a band gap of 1.575 electron volts measured from the highest point in the valence band to the lowest point in the conduction band, shown by the green arrow here. Bulk zinc oxide has a band gap of 3.37 electron volts, which is proved by previous research. With the evidence of our computation and other researchers' work, band gap can be decreased by decreasing the size of crystallites. The band gap represents the minimum amount of energy required for electrons to become excited, thus increasing conductivity. Therefore, we want the band gap to be as small as possible. The band gap of zinc oxide nanotubes is less than 2 electron volts, making it a viable choice. Experimentally, it's difficult to obtain the theoretical 1.575 electron volt band gap, but nanomaterials will help us get closer to it. Low conductivity makes it difficult for lithium ions to disperse through the materials. As shown in this figure, zinc oxide nanotubes are tested by SEM. If we look at the low resolution image of only 100,000 times magnification, it can be seen that the distribution of nanotubes is roughly uniform. There aren't too many large clumps of nanotubes, which would decrease their effectiveness. From the high resolution 200,000 times magnification image, we can see that the length of the nanotube ranges from the shortest at around 50 nanometers to the longest at around 250 nanometers. The width of the nanotubes is around 15 nanometers, which makes the aspect ratio around 5 to 15. Their length and thickness are both controlled by the pH of the liquid used. Strong bases with higher pH values cause the nanotubes to be longer and have thinner walls. Conversely, stronger acids with lower pH will cause the tubes to be shorter and have thicker walls. The time the mixture stays in the chamber also plays a role in its shape. The density of nanotubes on average will increase with time inside the chamber. The ideal conditions have to be determined experimentally. Finally, in this figure, the nanotubes are a lot more stable than simple bulk zinc oxide. The bulk zinc oxide specific capacity is higher than the nanotubes for the first few cycles, as you can see in the figure. However, it steadily decreases until around cycle 80, where it starts to drastically decrease. The specific capacity for nanotube zinc oxide, however, is steady at 861 milliamp hours per gram. The initial Coulomb efficiency is obtained by dividing the charging specific capacity of the second cycle by the discharging specific capacity of the first cycle. From the graph, we can see that the initial Coulomb efficiency for zinc oxide nanotubes is less than the initial Coulomb efficiency of bulk zinc oxide, which are around 0.655 and 0.752 respectively. This can be explained through the structure of zinc oxide nanotubes with more area. The specific area for the nanotubes is a lot greater than the specific area of bulk zinc oxide, which means there are more points of contact for the lithium ion to bond to on the nanotubes. As a result, more lithium ions become trapped in the anode as well, causing a greater decrease in the initial specific capacity to form an SCI film. After this initial drop, the zinc oxide nanotubes consistently outperform the bulk due to their greater stability and smaller volume expansion. This can be seen by comparing the reversible capacities, which is found by dividing the discharging specific capacity of the last cycle by the specific charging capacity of the second cycle. These values are 93.74% for the nanotubes and 62.73% for the bulk, showing that the specific capacity of the bulk drops significantly after many cycles. This can also be seen by looking at the variation in the Coulomb efficiency, which is the gray line. There's a much greater fluctuation of Coulomb efficiency in the bulk, while it's fairly flat for the nanotubes. So in conclusion, in our experiment, a zinc oxide nanotube model was constructed and the band structure and density of states of the nanotube were simulated using the model. The simulation results had a very small band gap indicating good electron conductivity, inspiring the nanotube experiment. Zinc oxide nanotubes were fabricated with hydrothermal reactions to test the simulation results. The fabricated nanotubes exhibited excellent cyclic performance. The reversible capacity of nanotubes is better than bulk by far, which are around 64% and 63% respectively. This Coulomb efficiency is also far more stable. However, in our study, only pure zinc oxide nanotubes and a simple model were tested. Better results might be possible with the addition of doping materials or different types of nanostructures, such as nanospheres or nanowires. The performance of the nanotubes might also be improved under a different set of hydrothermal conditions during fabrication. Here are the references we used for the study. Thank you for listening.